Hello students and friends. In this video, I will be analyzing problems related to hydrostatics, specifically hydrostatic pressure and Archimedes' principle, also known as the law of buoyancy. Our first question. In the manometer tube shown in the figure, the oil in the right-hand arm is olive oil of density 916 kg per meter cube. Letter A. If the top of the oil is 25.0 centimeters above the bottom of the tube, what is the height of the top of the water above the bottom of the tube? Letter B. What is the gauge pressure 15.0 centimeters beneath the surface of the water? Letter C. At what depth below the surface of the oil is the gauge pressure the same as in part B? So in our sketch or diagram, we have here uh, what we call a U-tube manometer, all right, which contains the two liquids. On the right hand arm, we have olive oil, whose height from the bottom is labeled as H sub oil. And on the left arm or left hand arm of the manometer, there is water, whose height from this level to the bottom of the manometer is not known. That is what we are going to determine in question letter A. Both ends of the manometer are open to the atmospheric pressure labeled as P naught. Alright, so since the two liquids are immiscible, meaning if they are mixed, they are not going to mix with each other, so there is a separation or a boundary labeled here as point P. Alright, and since water is denser than oil, we expect that the height for water, okay, from the bottom of the manometer will be lower compared to the height of the column of oil uh, in the right hand arm. Okay. Our solution for the first question, letter A, we wish to determine the height of the water column. So this is based on the concept that the pressure is the same at all points at the same level in a fluid at rest. Right? So consider the two fluids, water and oil, to be in static equilibrium. So they are not moving, they are not flowing from one point to another, they are completely at rest. So if we are to describe the pressure at the bottom of the manometer or at point P, the two pressures are just equal. Okay, the pressure of the water, we call it the gauge pressure, is determined by just using the formula density of water multiplied to GH, where H is the depth of the column of water. And that for oil, the gauge pressure for oil is also the product of its density times G and the depth of oil. If you're going to add to the gauge pressure, the atmospheric pressure, then we are describing the total pressure, also known as the absolute pressure. So the absolute pressure, for example, at point P is just equal to the sum of atmospheric pressure P naught plus the gauge pressure of water, or is also equal to the sum of the atmospheric pressure P naught plus the gauge pressure exerted by oil. And this is the basis of our computation for letter A, determining the height of the water column. So we just equate this to the density of oil multiplied by the height of the column of oil divided by the density of water. Substituting, we have 916 kilogram per meter cube as the density of oil, multiplied by the given height of the column of oil, which is in meter is 0.250 meters, divided by the density of water, which we all know is equal to 1,000 kilogram per meter cube. Doing our math, we will get the value for the height, the unknown height of the column of water equals 22.9 centimeters. All right. So for letter B, determining the gauge pressure of water, we use the formula P is equal to density of water multiplied by GH, where H is the depth of the water. That means the distance below the surface, and that is equal to 0.150 meter. Multiply that to G, and to the density of water, we will get this pressure 1.47, okay, raised to the third Pascal or Newton per meter squared. This is the gauge pressure of water. And for letter C, right? Letter C is asking for the gauge pressure or for the height below the surface of oil, where the gauge pressure will just be equal to that of what we got in letter B, or 1,470 Newton per meter squared. So we just equate that to the gauge pressure of oil, which is its density multiplied by G, and the unknown height H. Solving for height H, we just isolate and we get 1,470 Newton per meter squared. Divide that by the product of 916 and 9.80, or 8,976.8. So we will get the required height, okay, below the surface of oil to be equal to 0.164 meter, or in centimeters, that is 16.4 centimeters. Our second problem. The small piston of a hydraulic lift has a diameter of 8.0 centimeters, and its large piston has a diameter of 40 centimeters. The lift raises a load of 15,000 newtons. Question letter A. Determine the force that must be applied to the small piston. And letter B. Determine the pressure applied to the fluid in the lift. So as you can see in the drawing, this is what we call a hydraulic lift. And over here is the small uh, piston, whose of course diameter is given. All right. Uh, and the bigger piston, okay, the diameter of which is also given. All right. So in a typical hydraulic lift in most uh, service stations, okay, this is how we show the schematic diagram. Okay. So the bigger piston is the one that will lift or raise, okay, uh, a car or a vehicle that is given the this particular service. Okay, so we are asked to find the force that must be applied to the small piston. So our concept for this problem is, of course, the application of Pascal's principle or Pascal's law, which states that a pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and the walls of the container. All right, so that means that if there is a force F applied here, okay, in the smaller piston, the amount of pressure, meaning the amount of force per unit area, okay, is transmitted throughout all points within the liquid, including the pressure exerted on the walls of the machine. Okay, so whatever is the pressure here, okay, will be the same as the pressure that will be exerted on the bigger piston. All right, and that is simply expressed in this equation. Okay, pressure is basically equal to the amount of force F divided by the area over which the force is exerted. Okay, so it is assumed that the force is directed perpendicular to the cross section or cross sectional area of the surface, such as that of the piston. All right, so when you get the ratio F1 over A1, okay, which describes the amount of pressure exerted over the smaller piston, that must be equal to the ratio F2 over A2, which pertains to the pressure exerted, okay, by the liquid on the bigger, uh, what we call piston. So this is the formula that we need in order to answer the first question, or letter A. Okay, so that is, we isolate F1 and our equation becomes F1 is equal to uh, area A1 multiplied by F2 over A2. All right, since we are given the diameter of the smaller piston, the area of a cross-sectional, or the cross-sectional area, uh, assuming that the piston is cylindrical in shape, is actually equal to pi r squared. Okay, where r is the radius. Okay, but in here, since the same formula will be also used for describing the cross-sectional area of the bigger piston, so for simplicity, we just use the fact that the diameter is twice the area, twice the radius. In other words, there is no need to determine the radius. All right, we just directly use the value of the diameter, but we have to square it. All right, so in doing that, the same thing will be done for the bigger piston. The area is also expressed in terms of the given diameter, but the need to square it is important. Okay, uh, the what do you call this? The constant pi, okay, will simply cancel out. All right, and whatever is the radius, okay, for example, if we're going to insist on using the radius, that will be 8 centimeter divided by 2. But we also do that for the bigger piston. So the constant 2 will also be cancelled. All right, so it is but logical that our equation here, because we want it simplified, okay, using only the given diameter, but of course, uh, the diameter in centimeter has to be converted to meter before we square each of this given diameter. So doing our math, we will arrive at our answer for F1, which is 600 newtons. That's our answer to letter A. For letter B, determine the pressure applied to the fluid in the lift. We can either use the pressure exerted on the smaller piston or on the bigger piston. We expect to get the same. All right. So let's see. All right. So we use the pressure exerted, okay, on the smaller piston, and that is equal to F1 divided by A1. Okay, substituting, we have already obtained the value for F1, which is 600 newtons divided by the area A1. This time, there is a need to really describe the area in terms of pi r squared, all right, which is, of course, pi multiplied by the radius of the smaller piston, and that is 0.040 meter, then square it. So again, simplifying, the value for the pressure will be 1.2 times 10 to the fifth power Newton per meter squared. That will be the amount of pressure that is exerted, okay, to the fluid in the lift. All right, and that pressure is also transmitted equally in all parts of the hydraulic lift, including the pressure that is exerted here on the bigger piston, okay, that will be able to hold or lift a heavy load such as the car. Question number 3. A cube of volume 5.50 times 10 to the negative 3 meter cube and density 7.50 times 10 to the third kilogram per meter cube hangs from a cable, as shown in this sketch. When the cube has the lower half of its volume submerged in an unknown liquid, the tension cable is 375 newtons. Question is, what is the density of the liquid? Okay. Ignore the small buoyant force exerted by air on the upper half of the cube. So, the concept here is, of course, Archimedes' principle, or the law of buoyancy, which can be described in two ways. The first one is uh, as shown in equation number 1, that the buoyant force Fb is just equal to the product of the density of the liquid multiplied by the volume, capital V, referring to the volume of the liquid that is displaced by the submerged solid, and of course multiplied by constant acceleration due to gravity. So that's the first uh, definition of buoyant force. The second is in terms of the weight of the object, okay, in air, and its weight when immersed in a liquid or water. So we have this specific formula to determine the buoyant force that is exerted on a solid that is either partially or totally immersed in water. We just get the difference. Weight of the object in air minus its weight in water. So for this particular problem, uh, we first find the weight of the object in air, okay, because we are given the density and the volume, all right? If we multiply the density and the volume, okay, times the acceleration due to gravity, then we will be describing, or we will be getting the weight of the object in air, all right? So this weight in air is just equal to rho gv, and substituting for the density of the cube, which is 7.50 raised to the third, uh, this is the density, okay, of the cube, which is 7.50 raised to the third kilogram per meter cube, multiplied by 9.80 meters per second squared, and the given volume, which is 5.50 raised to the negative 3 meter cube. So again, simplifying, you will get this weight of the object in air equal to 404 newtons, right? Notice that all the units of our given quantities are in SI units. So our unit for the weight, of course, must be in Newton. So this is just the preliminary part of our solution. After getting the weight in air, all right, our next task is to find the buoyant force using equation number 2, all right, where the buoyant force is equal to weight in air minus weight in water. All right, since we are given uh, we are given this information that when the cube half of the volume of the cube is submerged in the liquid. Okay, so since the object is tied, okay, to a measuring device such as a force or spring balance, which reads 375 newtons, it it goes to show that this 375 newtons is the measurement in the spring balance, okay, which determines the weight of the cube when it is immersed or submerged partially in the liquid. So we interpret that 375 newtons as the weight, all right, the weight of the cube in the liquid, all right. So from our formula, weight in air minus weight in the liquid, we just get the difference, 404 newtons, all right, minus 375 newtons, and we get 29 newtons. What is this 29 newtons? This is the amount of the buoyant force, all right, exerted by the liquid on the solid, which is also equal to the weight, okay, the weight of the amount of liquid that has been displaced. So that is the meaning of buoyant force. We now use equation number 1 to determine, okay, uh, the unknown variable, which is the density of the unknown liquid. Okay, so our formula is simply equal to, okay, density is equal to the amount of buoyant force divided by the volume of the liquid that has been displaced multiplied by g. All right, so this is the derived equation based on the fact that buoyant force is equal to the product of the density of the liquid multiplied by the volume of the liquid displaced and acceleration due to gravity. And since we are looking for the density of the liquid, our equation or working equation will be FB divided by VG. And substituting, since we got already the buoyant force 29 newtons, divide that by the amount of liquid displaced, which is just equal to the volume of, or half, half of the volume of the cube. The total volume of the cube is 5.50 times 10 to the negative 3 meter cube. We get half of that, and that is equal to 2.75 times 10 to the negative 3 meter cube. And then multiply it by acceleration due to gravity, 9.80. So again, doing our math, we will arrive at this value for the density of the unknown liquid, which is equal to 1.1 times 10 to the third power kilogram per meter cube. So this is the density of the unknown liquid. Question number 4. A large plastic cylinder with mass 30.0 kg and density 370 kg per meter cube is in the water of a lake. A light vertical cable runs between the bottom of the cylinder and bottom of the lake and holds the cylinder so that 30.0% of its volume is above the surface of the water. What is the tension in the cable? As shown in our sketch, we have here the cylinder that is attached to a cable. Okay, the cable is holding the cylinder or preventing the cylinder from moving or floating, okay, on the surface of the water. Because if you notice, uh, this cylinder, plastic cylinder, is less dense compared to water. Its density is only 370 kilogram per meter cube. Okay, so that is less than the density of water. So we expect this cylinder to float in the water. All right. But in this situation, 30% of its volume is above the surface because it is being held by a cable that is attached to the bottom of the lake. All right. In other words, there is a force exerted on the cylinder coming from the cable. We call it the tension force. The tension force is directed downward because it is preventing the cylinder from moving to the surface. So, you notice there are two forces acting on the cylinder and both forces are directed downward. The tension force of the cable and the force of gravity, mg, which is the weight of this cylinder. The only upward force is the force, buoyant force, exerted by the water on the cylinder. And it is understood that the cylinder is at rest, so it is in static equilibrium. All right? So our analysis for the forces acting on the cylinder is such that the upward force must be equal to the two downward forces. So later on, we're going to calculate for that value of the tension force. But first, we have to determine uh, the volume of the cylinder given its mass and its density. See, we just divide the mass, which is 30.0 kilogram, by the density of the cylinder, 370 kilogram per meter cube, and we get 0.081 meter cube. This is the density, the volume, total volume of the cylinder. Okay, 30% of that volume is exposed or above the surface. That means 70% of the total volume of the cylinder is submerged in the water. So we calculate for that by simply multiplying 0.7 by 0.081 meter cube, and we get the volume of the cylinder that is submerged in the water, 0.057 meter cube. Okay, because this volume also represents the volume of water that is displaced by the solid cylinder. Okay, we need that so that we can determine the force, buoyant force FB exerted by water on the cylinder. Using the formula, FB equals density of water multiplied by Vg, where V is the amount of water that has been displaced. Alright, so substituting, we get density of water, as we all know, is 1,000 kilogram per meter cube, or 1.0 raised to the third power. Multiply that by V, which is the amount of water submerged, the amount of volume of the solid cylinder that is submerged in water, or the amount of water that has been displaced. So 0.057 multiply also by 9.8 meter per second squared, and we get this buoyant force equal to 559 newtons. All right? And lastly, we now get the amount of the tension force in our diagram. The tension force T can be isolated, so we will have the equation T is equal to the upward force FB minus the force of gravity mg. All right? And substituting the force of buoyant force, earlier determined as 559 newtons, minus the product of the mass, the cylinder, which is 30.0 kilogram, multiplied by 9.8 meter per second squared. So we will get as the value for the tension force equals 265 newtons. This is now the last question, number 5. A cubical block of wood, 10.0 centimeters on a side, floats at the interface between oil and water with its lower surface 1.50 centimeters below the interface. The density of the oil is 790 kg per meter cube. Question letter A. What is the gauge pressure at the upper face of the block? Letter B. What is the gauge pressure at the lower face of the block? And letter C. What are the mass and density of the block? Right, so in the diagram, as you can see, uh, two liquids, okay, oil and water. Since oil is less dense than water, and the two liquids are immiscible, in other words, they don't just mix together, okay, there is an interface between the two liquids. And there is a block of wood, as you can see again, okay, that is occupying that certain, what we call space, okay. More of the volume of the wood is surrounded by oil, and only a small amount is surrounded by water. All right. And we are given the depth or the height of the liquid oil, which is 10 centimeters, and also the depth of the water happens to be the same, 10.0 centimeters. For our first question, we are to determine the gauge pressure at the upper face of the block. Alright, so this upper face of the block is under pressure, okay? And the pressure is due to the presence of a certain amount of oil above, alright? So in our calculation, okay, we determine that pressure P, alright? Simply using the formula hydrostatic pressure equal to the density of oil times that depth H and of course G. So the density of oil is 790 kg per meter cube. Okay, we are interested on the amount of pressure for that particular height. If the total depth of oil is 10.0 centimeters, all right, and that according to the problem, 1.50 centimeters, okay, the lower surface of uh, the lower surface of the wood or that particular portion of the wood is under water. So whatever is that amount of depth, okay, must also be equal to 1.50 centimeters. All right. This distance or depth, okay, of oil representing the height, okay, the height of the oil above the upper what we call face of the block is equal to 0.0150 meters. We just converted 1.50 centimeters to meters. All right. So that is the height that we are going to consider. Okay. We are only interested in that depth of the oil from the surface up to that upper face of the wood. Okay. At that upper face of the wood, the pressure is expressed in terms of this equation. So when we substitute and simplify them, we will get the pressure being equal to 116 pascals or Newton per meter squared. So that's the answer to letter A, the gauge pressure at the upper face of the block. Now, for letter B, what is the gauge pressure at the lower face of the block? Okay, this time, we are to determine the pressure exerted by not only by the water, all right, but also the pressure exerted by oil. So if you notice, our formula is P at that point, the lower face of the block, is equal to the gauge pressure exerted by oil plus the gauge pressure exerted by water, all right? So since a common quantity is acceleration due to gravity, so I just factor it out, all right? And then we'll just add density of oil multiplied by the given height h, which is 0.100 meter. So we are considering the entire depth of oil, all right? That entire depth of oil, okay, determines the amount of gauge pressure exerted by oil, all right? But for the pressure exerted by water, we only consider 0.150 meter, all right? Because we are only interested on this particular depth from the surface of the water up to that level, okay, the level where the lower face of the block is located. And that happens to be uh, 10 centimeters minus, all right, that particular depth is exactly equal to 0.0150 meter, all right, that was given earlier. So upon substitution and computation, we will get this uh, gauge pressure for each liquid or exerted by each liquid. 774 Pascal, this is for oil, and only 147 Pascal, okay, is exerted by water. But if we get the total, that gives us 921 Pascal as the what we call gauge pressure at the lower face of the block. Our solution for letter C will be shown in the next slide. For question letter C, we first find the volume of the block or cube. So that is determined by just getting the cube of its side, which is expressed in meter, is 0.100 meters. So the cube of that is, of course, equal to 1.00 raised to the negative 3 meter cube. Okay. The next step is for us to determine the volume of the oil that has been displaced. All right? And that is just equal to the product of uh, the two sides, which is 0.100 meter, multiplied by the depth, which is 0.085 meters, and we will get this volume of the amount of oil that has been displaced. It is equal to 8.50 raised to the negative 4 meter cube. Okay, once we know this, we can now determine the force FB, or the buoyant force exerted by the liquid oil on the block, which is actually also equal to the density, all right, the density of oil multiplied by the amount of oil that is displaced and acceleration due to gravity. So that is equal to 6.58 newtons. Now, for the amount of water that is displaced, we did the same procedure, multiply the two sides of the block and the depth of water. All right. So this amount of volume of water displaced, which is equal to 1.50 times 10 to the negative 4 meter cube. Okay. Uh, we need this to be able to calculate for the buoyant force exerted by water, okay, on the block of or the cubic block, and that is FB is equal to the density of water multiplied by the amount of water displaced or the volume and G. So we get the answer FB is equal to 1.47 newtons. Next, we determine the total force FB. This is the total FB, 6.58 newtons plus 1.47 newtons or 8.05 newtons. By definition, the buoyant force exerted or the total buoyant force exerted by the oil and the water is just equal to the weight of the cube. So, we can now determine the mass of the cube, which is just equal to the weight divided by G, or 8.05 Newton divided by 9.80 meters per second squared. So we get the mass of the cube or the block, which is equal to 0.821 kilogram to 3 significant digits. And finally, the density of the block, which is mass over volume, and that is equal to the mass, which is 0.821 kilogram divided by the volume of the block, which was earlier determined as 1.00 raised to the negative 3 meter cube. All right, so the density is equal to 821 kilogram per meter cube. So that's about it. Thank you very much for watching.